It's a pleasure to welcome Sergey Levine, who is here at Berkeley. Sergey got his PhD at Stanford and has worked at University of Washington and at Google. And he's done all sorts of exciting work on reinforcement learning, deep learning, and particularly applications to robotics. So we're very happy to have him talking today.
Thank you for the introduction. So yeah, a little bit about myself. So I'm an assistant professor here at Berkeley. In my lab, we work on a lot of problems in robotics, a lot of kind of core algorithms problems in reinforcement learning, and the full range in between. So one of the things that I really enjoy in this line of work is to design an interesting algorithm and actually take it all the way from kind of the foundational kind of work to design the method all the way to an application on a real physical system. So these are just some of the videos of the kind of robotic systems we've worked with. Arms, manipulators, mobile robots like drones. This is a video of a tensegrity robot that we worked on in partnership with NASA Ames. So there's kind of a range of different systems that some of the methods that I'll describe today can be applied to. But before we get into that, let's kind of back up a little bit and talk a little bit about some motivation. So a few days from now, you'll see a talk from Russell Khudinov on deep learning, and some of you probably already know quite a bit about this topic. So we've seen, for example, in domains like computer vision or other passive perception domains, that deep learning methods have made a really big impact in recent years. And one way we can kind of look at what the benefit of these methods has been is as following. If you think about kind of the state of computer vision maybe 5-10 years ago, the way people typically thought about vision would look something like this. You have an image that you give to the computer that consists of pixels, and then you're going to extract some features from this image, some hand-designed features like a histogram of oriented gradients. On top of those features, you might extract some other set of higher-level features like a deformable parts model. And then on top of these, you would build your classifier or detector or something that actually learns how to pick out the thing that you care about in the picture. And with deep learning, the story is actually very, very similar. You still have different layers of representation. It's just that now these different layers of representation here are not designed by hand, but they're actually learned from the data. So the benefit is that now we don't have to manually engineer the right kind of features here in the middle. And the representation is actually adapted to the particular task we want to do instead of kind of requiring really, really smart graduate students to sort of design the best universal feature for whatever vision task we might want in the future. And it actually turns out that if we do this right, the kind of features we might learn are somewhat generic, but we have good confidence that they'll be particularly suited to the tasks they're trained on. But that's the passive perception side of the story. If we want a machine learning system that actually does something in the real world, essentially, by definition, if it's doing something, it's making decisions. So it's very good if we can automate the process of building the features and train good features that are suitable for what we eventually want to do. But in the end, there's going to be kind of a whole other side to this cycle. So if we're let's say, perceiving the tiger in the forest, we'd like to also know how we can use the output of what in this case is an image classifier to actually make a decision about what we'll do next. And in reality, for any system that's actually deployed in the real world, that's actually doing something and making decisions, typically the decisions it's making are going to affect what it sees next. So there's actually, whether we model this or not, there's going to be a perception action loop, whether the system is a robot or a website that's interacting with users or anything in between. If it's making decisions, that part of the cycle actually exists, and perhaps it would be a good idea for us to reason about it. So there's something that looks like perception, interpreting the data, and something that looks like action, basically using that interpretation to decide what to do. And what I'm going to discuss in this talk is how we can actually close the loop on perception and action and consider them jointly. So that instead of designing kind of a pipeline that tells us something about what we're seeing, and then another pipeline that uses that to decide what to do, we can train them all together. So why is this something that we might want to think about? Well, one reason we might want to think about it is that there's sort of good evidence that the way that people make decisions very closely couples perception and action. So maybe from an intellectual standpoint, that's something we want to consider. This is an example that I like to give of this. So this is an athlete catching a ball. And there's a famous evolutionary biologist named Richard Dawkins who wrote in his book sort of his interpretation of this phenomenon. He wrote that when a man throws a ball high in the air and catches it again, he behaves as if he had solved a set of differential equations in predicting the trajectory of the ball. And at some subconscious level, something functionally equivalent to mathematical calculations is going on. So this is sort of the perception and the action. So you perceive, you model how the ball is going to go, you determine its landing point, and then you act on that interpretation and plot the course so that you can catch it. And then in the 90s, scientists actually studied how it is that people actually do this, and it turns out that it's actually quite a bit simpler. So it turns out that all we do is we look at the ball, and we look at where it is in our field of view, and we fix that position. We stare at it, and then we start running. And if the ball drops a little bit, then we speed up, and if it rises a little bit, then we slow down. And if we follow this very simple heuristic with a rudimentary kind of similar triangles argument, you actually prove that you'll arrive at exactly the spot where the ball lands. So you don't need to estimate your air velocity, you don't need to estimate gravity, nothing at all. As long as you tightly couple perception and control, you're going to be able to do the task.
And isn't that, professionals just have optimized this little policy better than the average person? Or?
Not just professionals. I mean, animals can do this too. I mean, there's obviously a lot more to it. You also have to be really quick on your feet. But there's been studies that show that, like frogs, for example, use a similar kind of gaze heuristic. If you apparently, I don't know this firsthand, but apparently when you learn to fly an airplane, one of the things they teach you is if you want to determine if you'll collide with something, look for a spot of dust on the windshield, and if it's stationary relative to the other airplane, then you're on a collision course. So it's a heuristic that sometimes is taught and you can kind of process it cognitively, and sometimes it's subconscious in the case of the ball catching. Okay, so why is this kind of relevant? Well, it shows that you can couple perception and action very tightly, shortcut this really complicated pipeline, and actually do better. So if we can autonomously acquire these kinds of sensory motor skills, then perhaps we can do very well without having to solve this really complicated perception problem, this really complicated decision-making problem, and kind of shortcut them and do better. Here's a robotics example to also motivate this idea. This is a video of a very successful robotic system. This is a competitor in the DARPA Humanoid Robotics Challenge that was held in 2015, and this is a team from South Korea, from KAIST, that actually won the contest. So this was the best performing robot in the competition. It actually accomplished all of the tasks that were set out before it. And here this robot is performing the door opening task. It does actually open the door eventually. It takes I think about a minute and 40 seconds to do this. So it's very successful. There's actually a lot to be impressed by in this video, and I think any roboticist watching this will kind of will agree with that. But from sort of the third-person perspective, it does look distinctly robotic. And to prove to you that it looks distinctly robotic, let me show you a colleague of mine from grad school named Philip Kronbuhl performing the door opening task. And here's how Philip does. He's very quick. He's a computer vision professor at UT Austin now, and you might think that, well, he has very good vision skills, right? So he's using his binocular vision and hand-eye coordination. But actually, he's doing this blind. So clearly, Philip is way ahead of the robot, much quicker, and apparently with less sensory information. So in this talk, I'm going to talk about methods that will allow us to learn sensory motor skills end-to-end. And from a robotics standpoint, kind of the vision here really is that, well, in computer vision, we saw this transformation from having to design different stages in a pipeline to learning that entire pipeline. Well, what if, kind of thinking about this naively, what if in robotics we can have the same thing? So the robot that you saw, the robot in the DARPA contest, I don't know exactly the details of how it worked, but generally robots of that type have kind of a pipeline approach to control, where there's different modules, often actually designed by different teams that are all wired together, performing this task. And if we can actually learn that entire cycle end-to-end, perhaps we can do better. Perhaps we can make use of the same kind of properties that make the ball catching heuristic work better, or that allow Philip to open the door so quickly. So at a very broad level, we might imagine that the way we might control a cyber-physical system like a robot is that we might have inputs from the sensors, like the camera, feeding into some learned model, which may or may not be a deep neural network. I'm drawing it here as a deep neural network because those are the experiments that I'm going to show you. But so long as it's learned and it's end-to-end, that's going to be good. And then it directly outputs the actuation commands, which then go to the robot's motors. So this is essentially the robot sensory motor loop. Now, drawing it in this way makes it look kind of simple. In reality, there's a number of big challenges that make this quite a bit tougher than just sort of the n+1th application of deep learning, because for a task like this, our supervision is going to be very indirect. So you can't just ask a person to directly tell the robot, here are the torques you should use. For some systems you can, and I'll talk about that a little bit. For example, for cars you can get fairly good direct supervision, but for some systems you can't. And the other problem is that the actions have consequences. So if you want to control a system like this, you really have to reason about the fact that your data is not going to be IID anymore. The action you take is going to affect the next observation you see, and if you don't account for that, then you'll have a bad time. So we need algorithms that can actually take care of it. I care about this stuff because I want to make robots actually do useful things in the real world. But even if you don't care about robots doing useful things in the real world, I'm going to make the case, hopefully, that this is something that you should care about. Partly, I think we should care about it because I think studying these kinds of questions will help us understand human intelligence, because humans do have to reason about both perception and action. And I think studying how we can close this loop can help us understand that. I think that beyond robotics, a lot of the kind of algorithms that we might develop for systems that perceive and act in the real world and actually reason about the consequences of their actions can help us build other interactive systems. For example, if you imagine a personal assistant on your cell phone, that's a system that has to perceive the world, process the sensory information, make a decision, and then reason about the consequences of that decision. Or if you imagine something like, for example, a smart power grid that has to deal with energy generation, storage, variable demand, and so on. That's a system that has to perceive the world, take actions, and if we have sort of an end-to-end approach that reasons about that, then maybe we can do better. Okay, so that's kind of the motivation. Now let me tell you about the goals for today's lecture. I'm going to introduce some formalisms of decision-making. Emma Brunskill talked about reinforcement learning earlier today, so she might have mentioned some of this as well, but I just want to kind of go through the definitions and make sure that we're all on board with that. So I'll talk a little bit about that, probably pretty quickly. I'll talk a little bit about some recent research, specifically topics like imitation learning and reinforcement learning, and then I'll talk about some outstanding research challenges and hopefully get across some idea of what is easy in this field and what is hard, and where we could go next. Okay, so let's start with imitation learning. For those of you that were here for Emma's lecture or already know some of this stuff, I apologize if this starts off kind of basic, but I just want to make sure we're on board with all the definitions. So in kind of a classic supervised learning setup, we have some kind of input and we have some kind of output, and I'm just going to call the input O for observation. I'm going to call the output U. And then we're going to build some kind of model that predicts the distribution over U conditional on O. Right? In a sequential decision-making setting, we're going to have a sequence of observation and a sequence of actions. So we'll put these little subscripts T on everything to get that across. And the action that we take is going to affect the next observation. So instead of classifying this image with a semantic label, we might have a selection of actions, maybe a discrete selection, or maybe a continuous selection, like we can decide which way to run when we see the tiger. So the terminology, O stands for observation, U stands for action, and pi we're going to call the policy. So that's just a distribution over action, conditional observations. In general, it might even be conditional on a history of observations, so that's kind of a generalization of this. But for now, let's just talk about reactive policies that are conditional on the current observation. Now, one of the things that we have to also introduce to really understand what the problem setup is this notion of state. And it's important to understand the distinction between state and observation. So if you imagine a picture like this, let's say that you're a robot and you see this picture. It consists of pixels. That's several thousand dimensions. That's your observation. Underlying this, there is a state. So there is some underlying dynamical system that gives rise to this image. So it might be the position of the cheetah and the position of the gazelle. And that's the state. So formally, the thing that distinguishes the state from the observation, well, I'll skip this part. Formally, the state that distinguishes them is if you actually draw the probabilistic graphical model, the state is going to have this interesting conditional dependence property. So the state at time t plus 1 is independent of the state at t minus 1, conditional on state t. And this is called the Markov property. So the state obeys the Markov property, meaning that if you know your current state, that's all you need to know about your history. The observation in general does not. So in the general partially observed case, we'd like to get policies that work in response to observations, but we have to remember that an observation alone might not be enough to tell you everything about where you are, that really the thing that has that independence property is the state. So that's just a little bit of definitions and notation. So now let's talk about imitation learning. So I kind of originally drew this picture and I said that, well, this is, we start with an image classifier and then we'll just replace the output. Instead of being a semantic label, we'll call it an action. And we can actually do learning this way and actually learn how to control dynamical systems, and we can see what happens. So maybe instead of this example with the tiger, let's say that your observation is an observation from a dashboard camera of a car, and your output now is going to be a steering command for the steering wheel. So U is going to be, let's say, a two-dimensional vector where the first number corresponds to how much you turn the wheel, and the second one maybe corresponds to whether you push the gas or the brake and how much. So we can say, okay, well, that seems pretty familiar to us. Let's just tackle it the same way that we tackle our standard supervised learning problems. Let's get a person, let's say a human driver, to drive a car around, collect lots of data, collect lots of O's and U's for us, stick those O's and U's into a bucket, call that our training data, and then train our favorite, computer vision model, let's say some convolutional neural network with supervised learning, so that it gives us a distribution over O's, over U's, condition on O's. So kind of the simplest thing we could do using, let's say, some standard computer vision software. Okay, well, that seems like a reasonable place to start. So does it work? Well, the theory in general says that probably not. And there's a good kind of intuitive reason to, I won't go into too many of the proofs here, but there's a good kind of intuitive explanation for why the answer ought to be no. So let's say that this is our training trajectory. So I'll show a few of these plots in this talk where one axis is state. You can imagine like a one-dimensional state. Another axis is time. And then we can kind of think of this as a trajectory, an example trajectory. In general, there might be more than one, but let's say there's one for now. So we take this example trajectory. This is what the human driver did. We're going to train our policy pi on that, and then we'll run that policy. And when we run that policy, it's not going to be perfect. It's solving some regression problem. In general, anytime you solve a difficult regression problem, you have some small epsilon error. So because you have that small epsilon error, your policy will make some small mistakes, and it will find itself in states over here that are a little bit different than the states that it saw along the training trajectory. And when it finds itself in those states that are different from any of the states it saw in the training trajectory, it'll probably make a slightly bigger mistake. And then it'll find itself in a state that's even more off from the training trajectory, and it'll make an even bigger mistake, and so on. And these mistakes in general might accumulate, in general, quadratically in the time horizon. And I'll give you a citation later that talks about this. So the theory says that, there's not really any reason to believe that this will work. Okay. So let's look at an example from, maybe somebody who didn't care so much about the theory. This is a video produced by NVIDIA where they actually did this. They had a human driver drive around, and initially maybe it looks a little bit disappointing. The car does some scary things, freaks out the cameraman. And then they drive around a bit more, generate a bit more training data, and something seems to work. So at least to the point where this guy is comfortable pressing this button, at least for the duration of this video, and seems to still be alive. And as far as I know, no one was injured in the production of this. So, okay, that's kind of cool. I mean, it's a car, it's driving. So what's going on? Why is that seems to be a little odd, right? So we can try to understand what's going on here. I'll tell you that from kind of a theoretical standpoint, we don't completely understand, but I'll give you a few kind of initial hints. So if we look at the paper that was produced accompanying this research, we can find a little diagram of the system that they built. There are some cameras on the vehicle. Those cameras, the images from those cameras go into a convolutional neural network. That convolutional neural network, predicts what the steering command should be, and so on. And there's some adjustment, etc. But one thing that's maybe a little thought-provoking is that over here you have not one camera, but you have these three cameras. Okay, so what's going on there? Their network actually only processes one image at a time, but they have three cameras on their car. Well, it turns out that this is what they did. They have a camera that faces forward, and they record the images from that camera, and they label it with the steering command that the human actually executed. Then they have a camera that faces a little bit to the left, and they label the images coming from that camera with the steering command that the human executed, plus a small offset to the right. They have a camera that faces to the right, and they label it with a steering command that has a small offset to the left. So now, when their policy makes that little mistake, it doesn't find itself in a state that it's never seen before. It actually finds itself in a state that's somewhat representative of the situations that it saw from these sideways-facing cameras. So when it starts to drift a little off the road, it sees the view that maybe the left camera saw. And now the supervision for that was to turn right. So from this, you can actually get a controller that stabilizes the car and keeps it in its lane. That's very interesting. And the word stabilizing might be a little thought-provoking because in the world of optimal control, we deal with notions of stability quite a lot. So maybe that's kind of part of the explanation here. And indeed, in some of the experiments that I've done, one of the things I found is that if you have a training trajectory that you get maybe from a human demonstration, and then you can somehow build a trajectory distribution around it using a stabilizing controller that you obtain with optimal control, and I'll get into some of the details of this a little bit later in the talk. You can take that optimal controller, you can generate samples where you introduce some perturbations, ask the controller to compensate for those perturbations, and use that to augment your data set. And if you do that, and then you train your policy with supervised learning, it tends to work quite a bit better. But I don't have a proof that this is always going to happen. But it seems to work better.
Side cameras only for training, and when it's actually used.
Correct. So that tells you maybe something about stability is at play here, and I don't have a concrete answer to that. That's one of the questions I'm going to pose to you guys later on. I'll skip this part, but I'll show you just a result. So this is a video of a full physics simulation of a humanoid, 3D humanoid running on uneven terrain. That was, the humanoid here is controlled by a neural network that's at every time step taking in the state of the system and outputting joint torques. And the example here consisted of a motion capture sequence of a person running that was then augmented with a stabilizing controller to generate these perturbations to build a neural network that could actually stabilize the full 3D physical system. So that showed, and to me I think, part of the reason this works is actually very similar to the reason why the car driving stuff works. But more on this later. Okay, so that's maybe somewhat of an empirical result. Now, can we say a little bit more about how we can make this work more often that actually has a little more in the way of guarantees? Well, we can analyze this from kind of more of a probability standpoint, and we can try to understand, why is it that this red line will diverge from the black line? The explanation is actually fairly simple. So we have a policy pi u given O that is trained on some distribution over observations. And that distribution is your data distribution, right? When the human drives the car, they give you observations from some distribution, p data. But when you then run pi theta, u given O, the policy that you learned, it's going to see observations from some other distribution, p pi, that is induced by this policy. This distribution is not the same as this one because this is not the same policy as the one that the human executed. So the problem here then becomes pretty clear. You train on one distribution, you're testing on another one, so obviously it might not work. In the extreme case, if your car drives off a cliff, it's going to see something totally different from anything it ever saw. So of course, the support between these two distributions might not even be the same. So okay, can we fix that, right? If our problem is the distributions don't match, let's find a way to make them match. Let's find a way to make p data equal to p pi. Okay, well, one way we can do that is we can somehow make our policy perfect. If our policy is perfect, then it will have exactly the same data distribution. But that's hard. We can actually do something different. We can, instead of changing p pi, let's change p data. So instead of being clever about p pi, let's be clever about where our data comes from. And that's an algorithm proposed by Stefan Ross and Drew Bagnell from Carnegie Mellon called DAgger, or data set aggregation. And that's actually quite a simple algorithm that solves this distribution mismatch problem under a few assumptions, one of them being that you can actually ask a human for more labels. So let me describe this algorithm to you. So your goal is to collect data from p pi instead of p data. And the way you're going to do that is by running pi theta. So pi theta, when you run it, it'll give you observations from p pi. So that's how we're going to fix this problem. So but we're going to need labels for all those observations. So this is how the algorithm works. This is a simplified version. And in the paper by Stefan Ross, you can find kind of the full version. I'm going to present just a simplified version of it. So first, you're going to ask your human to drive the car, and you're going to get a bunch of observations and actions, and you'll do the standard imitation learning thing. So just train that pi theta in the usual way. And then you're going to run pi theta and collect a data set of observations that your vehicle will see under autonomous control, or your system in general. And then you'll just ask a human to go through all those images that the vehicle saw and tell you what the steering command should have been. And if you think this is a little bit weird, it's because it is, and I'll talk about that more later. But let's assume that we can sit a person down in front of a TV, give them a steering wheel, and just ask them to tell the vehicle how to steer the car. And then you're going to just combine these data sets. You're going to take this new labeled data set d pi, take the union of that with what you have so far, and then you'll repeat and retrain. And you just go through this over and over and over again. And sort of the full proof is in the paper, but the kind of the simple version is that as you do this more and more, eventually your data set D is going to consist primarily of data from your policy, and the whole thing will actually converge. And there's a more formal result in the paper. Okay, so we can kind of solve this distribution mismatch problem if we just run our policy on our system, collect more observations, and then ask for optimal labels for those observations. This is an example of this algorithm in action. So this is a policy trained using DAgger, controlling a quadrotor. This is a first-person camera from the quadrotor, flying through a forest and avoiding trees. And the bar at the bottom shows you the steering command outputted by the policy. This is actually using some hand-designed visual features, but since then they've repeated this experiment using deep neural networks as well, and that works perfectly well without hand-designed features. Okay, so what's the problem? Why might this not be enough in all cases? Well, there are a couple of problems. One of the problems is this, that in order for this algorithm to work, you need to be able to ask a human for these labels, which is a little bit unnatural. So you need to have a person sitting in front of this TV and turning the steering wheel. It'd be awfully nice if we could just get rid of the person there and just have a computer provide those labels. And that's what I'll talk about in the next section. So first, let's recap the imitation learning part of the talk. So imitation learning is usually but not always insufficient by itself. So there's some theoretical reasons to suppose this is the case, like the distribution mismatch problem. Sometimes imitation learning works well. Sometimes it just works well out of the box if you're lucky. Sometimes it works well because you have clever tricks to make it work, like the cameras thing. And sometimes your trick is to sample from a stable trajectory distribution. Or you can do something like use DAgger to actually solve the distribution mismatch problem. So there are a few kind of questions that this raises, and this is maybe my kind of posing the question for you guys if you have any thoughts on this. The distribution mismatch doesn't seem to be the whole story, because something like the NVIDIA result seems to suggest that if you just kind of provide some data that gives a notion of stability, that seems to work fine even without using something like DAgger. Imitation often works without DAgger perfectly well. And can we think of kind of a way to actually incorporate some notion of stability into a theory of imitation learning that actually tells us in which situation we might expect direct imitation to work and in which situations we might not?
Question?
Yes.
Can you say more formally what you mean by stability here?
So, well, I can't because I don't know. But my guess is that it's something like if the expert that is generating your data is following a policy that satisfies some stability conditions, meaning that if you start it within some range of states, it will converge to states within that range. Perhaps you can say something about what happens if you train a policy with imitation learning on that data, modulo some number of samples, etc. So currently, as far as I know,
so the human expert has a stable policy.
Probably you'd have to assume something like that. So my guess is that if you want to show something about imitation working well without requiring a fix to the distribution mismatch problem, you'd have to make additional assumptions about the expert, such as that they're following a stable policy. Because I think if you don't make any assumptions about the expert, then the trouble is that you can't even show that that when you try to imitate, you'll have, if you don't have anything in your policy class that can even come close to matching that, you can have arbitrarily large errors. So you probably need to make some additional assumptions about the expert if you're not going to be able to obtain more samples. So DAgger solves this problem by just getting more samples. Yes?
I mean, this is maybe a bit philosophical, but when you think about baby animals or baby humans learning, they basically follow imitation learning, but they don't have this kind of someone that will label for them unforeseen situations. So how do you think animals handle this problem?
So I'm not I don't study animal behavior, so I don't feel qualified to answer this. But one of the things I can kind of, speculate a little bit about is that imitation is more than just directly copying an action someone took. So that's sort of, in some ways, the simplest form of imitation. Imitation can be a bit more high level. It can be about, for example, copying someone's intentions. And there is some work that I don't think I have in this presentation, but it's some work that I've done and that others have done on actually inferring intentions from demonstrations. And that's interesting because when you infer intention from demonstration and then attempt to copy, attempt to find a behavior that satisfies that intention, then you're really combining both your observation of somebody else and your own experience. And when you combine your observation of someone else and your own experience, then you can, then you don't have to rely entirely on the demonstration giving you all the data. You can actually try things and see what works and use that to find a way to get to the right states. So that, I think, is a crucial ingredient of kind of true imitation. Okay, so the rest of this I kind of already touched on. Do we really need to add more data to make imitation work, or is there some way that we can formulate a set of conditions on an expert or on a data set from which we can say something about whether imitation will work or not? And if we can do that, that would be awfully nice, because asking for additional data after the fact involves some fairly unnatural data collection protocols and a lot of jumping through hoops. So if we could just grab a data set and be able to say, if it meets these conditions, imitation will work, that would be awfully nice. All right, so now let me talk a little bit about imitation without a human. So can we imitate an optimal control algorithm and take the human out of the equation? And then from that, we'll lead into reinforcement learning. So before I get into this, I need to introduce a little bit of an additional definition, which is, if we don't have a human giving us data, what makes an action good and what makes an action bad. So let's take out that policy for now and just try to write down a condition that says, what makes these U's good U's. So if I'm in this situation, I see the tiger, I need to decide which way to go. One thing I might want to do is minimize my log probability of getting eaten by the tiger. That's something that I would very much like, and that's conditioned on the actions that I'm going to take. So it's a sequence of actions, so I need to get away from the tiger now and then not come back to the tiger later. So I can more generally just say that I have some cost function, and I'm going to minimize that cost function over all time. And I need to add an additional constraint to this minimization, because these actions actually affect my state. So the constraint is that the next state is some function of the previous state in action. So this is the formulation of a classic optimal control problem with a cost function C. So that's the new thing I'm going to introduce, so that I can talk about whether actions are good or bad independently of whether I have any data from a human demonstrator. And then, kind of a classic way to deal with this kind of problem is to use a technique like trajectory optimization, which just says, write down this optimization problem and then find your favorite optimization algorithm that actually solves it. There are a number of ways you could go. For example, you could take this constraint, notice that it's an equality constraint, and you can just substitute it in there for all the x's, and then you get an unconstrained problem. That's good. There's a number of ways you can solve this unconstrained problem. You can also deal with the original constraint problem, so sequential quadratic programming methods are really popular for this. I won't get into these too much. I just want to kind of write down the problem and just say kind of generally how it can be solved. So that's the usual story. You differentiate through all this stuff and then optimize. And the main thing that you need in order to differentiate through this stuff is you need to know some derivatives. You need to know the derivatives of the dynamics with respect to the state and with respect to the action. And you need to know the derivatives of your cost. So if you have these, then there's a range of different optimization methods that you can use that'll let you solve this problem. In practice, for real-world trajectory optimization problems, it really helps to use a second-order method. First-order methods don't seem to work so well, partly because you have this function f being applied many, many times. But other than this, lots of different methods can help you with this stuff. All right. We can also write down a probabilistic version of this. So we can say that maybe our dynamics are not deterministic, maybe they're stochastic, maybe the next state is distributed according to some conditional distribution that depends on the previous state in action. So a simple stochastic dynamics for continuous systems that's often used is that your state is some Gaussian distribution where the mean is this thing f, and there's some covariance, some noise added. You can build a simple stochastic policy. For example, you can build a linear Gaussian policy. It's a linear feedback policy with some variance. And then this minimization of the cost ends up being a minimization of an expected cost. So the expectation is taken with respect to this distribution over states and actions, which is a big product over your dynamics and your policy and so on. So this is kind of how you can convert this into a stochastic control problem. So let me see here. So this picture that I drew for you before, this distribution over trajectories, when I talked about stability, that was actually illustrating with the running example, that was actually obtained using a stochastic linear feedback policy. So that there we were training this time varying policy that with optimal control that just basically looks at the current state, sees how much it deviates from the desired state, which came in the running example from the mocap data, and then applies some little feedback matrix to it, which you can optimize if you know the dynamics distribution up here. Okay, so that's all kind of, I'm not going to get into it too much because that's just kind of optimal control stuff. So the linear feedback just kind of pushes you towards that mean. And that's where the stability there came from. Okay, so can we use something like this in the context of, let's say, an algorithm like DAgger? And replace a human with a machine. Actually, in the original DAgger paper, they actually showed this just as a way to validate the algorithm. This was in a discrete example rather than a continuous one, so they actually used A*search to play Mario and then used DAgger to find a policy for it. But you can also do it with continuous methods. So I'll tell you about an algorithm now that uses this kind of continuous stochastic optimal control together with DAgger, but it has a little bit of an additional kind of property to it, which is that it's going to address another problem with DAgger that I didn't mention yet. And the problem is this, that besides needing to get actions from the human, you can fix this by getting the actions from the computer, but you also need to run pi theta. And this can be a bit of a problem. So if you remember this video from earlier, well, if you initially have a bad policy pi theta and you run it on your car, it's going to do this stuff. If you have a person sitting there with a button, that's okay. Maybe the person can stop it. But if the vehicle is autonomous and is just learning in the real world, then this can be pretty bad. So what I'm going to talk about now is an algorithm that uses optimal control to avoid the need for human labels, but it also solves this problem in step 2 by not needing to run a potentially unsafe, partially trained policy. So this is an algorithm called PLATO, which stands for Policy Learning with Adaptive Trajectory Optimization. And this was by my student Gregory Kahn, another student named Tianhao Zhang, and with my collaborator Peter Abiel. So the change that we're going to make in PLATO is a very small change. It's very similar to DAgger. But the change is that instead of running pi theta in step 2, we're actually going to run a different policy, which I'm going to call pi hat. And we're going to design this policy in such a way that we actually retain the convergence guarantees of DAgger, but avoid actually doing something potentially unsafe in the real world. And here's how we're going to do that. So pi hat is going to be this simple stochastic policy. It doesn't really matter so much what it is, but for in our implementation, it's a time-varying linear feedback policy, and it's going to be re-optimized at every single time step. So this is what's called in model predictive control in robotics. So every single time step, we're going to solve an optimal control problem, which means we're going to replan every time step, and our objective is going to be the usual objective, which is to minimize expected cost, but with an additional term with a little multiplier lambda on it that says minimize the KL divergence between the policy that you're going to optimize pi hat and the learned policy pi theta. So what this means is that if your car is in some state, it has an image, and your learned policy pi theta, your whatever convolutional network says, okay, you should drive forward. And you actually run this optimal control algorithm and you decide that driving forward is going to cause you to hit something. So then pi hat is going to say, okay, well the best I can do that's as close as possible to pi theta but gets low cost is to drive a little to the left. And then you're going to execute this policy pi hat for one time step. And now you're going to replan. So now you get a new observation. Pi theta now says, oh, okay, now I want to go right. So now you're going to replan, find a new pi hat, execute the first step of that, and continue this way. So why do we replan? So this is called model predictive control when you replan like this. Why do we replan? Well, it's because pi theta depends on the observation. And we don't necessarily know what the observation is going to be in the future. We can't predict what the camera images are going to look like. But if we have a decent dynamic model of the car, which you can obtain, you can reasonably predict what the state is going to be. So if you remember the distinction between state and observation, in this method, pi hat is a policy with respect to states, but pi theta is going to react to images. So yeah, that's what I just said. So if you remember this conditional dependence relationship, the states are conditionally independent, but the observations might not be. Okay, so that means that you need some way to obtain your state when you're actually training this thing. So you might have some external observer. Maybe there's a helicopter tracking your car, or maybe if you're learning to fly a quadrotor, maybe that quadrotor is flying in a mocap system, which we typically do anyway. So we assume we have some way to get an external observation of the system at training time so that you can actually solve this optimal control problem with respect to states. And then you assume you have known stochastic dynamics, but a potentially unknown observation function. And that's actually a fairly realistic assumption for things like autonomous cars, because autonomous cars are governed by relatively simple physics, but the observation function is the image generation process. So that's like, how do the image pixels depend on where the car is, which is very difficult to model. So you need to know where your states are going to be in order to solve the optimal control problem. but you don't necessarily need to know the observations, and that's why you replan every time. So that's the PLATO algorithm. Does anybody have any questions about this before I go on to the results? Yes?
I was not fully following, but you raised initially, and when you started the discussion, you raised the problem that if I have a human sitting there by the wheel, it could push an emergency button.
Yes.
How do you overcome this, arriving into a situation in which a mistake will be very costly? How does the system realize that it's there?
So one thing to note about this method is that all this stuff, this describes what happens at training time. So if at training time you have an external observer that can measure the state of the system, and you have an optimal control algorithm that, given that state, can plot optimal paths, that's what's going to prevent the bad stuff from happening. Now, the assumption that you know the true state of the system at training time is a fairly strong assumption. So if you have a car out in the wild, it generally won't know its own state. But if it's driving, on a closed course, maybe there's some kind of measurement system in place, or in the example I'll give later, if you have a quadrotor with a motion capture system, then at training time, you know where it is. At test time, once this pi theta thing is trained, then it can go out into the wild, and it doesn't require ground truth state measurements anymore. So the thing that basically ensures the safety is the fact that you're not ever running pi theta at training time until it's been fully trained. Now, this sort of goes hand in hand with the fact that this is in the context of this DAgger-like algorithm, because what the DAgger result tells us is that once we train this policy, it'll be a good policy. So long as we can ensure that we can make it a good policy without ever having to actually run it without this additional kind of safety mechanism of the optimal control algorithm, then we're in good shape. Yes?
So you talked about stability before. Somehow you're getting stability because you regularize and
No. So in this, the good performance of pi theta is coming from solving the distribution mismatch problem still. And the reason that that's happening is because pi hat is going to take actions that are close to pi theta if it's able to do so. So basically, and you need to show that lambda, follows some particular schedule. So there's a condition on lambda that you need to obey. But basically, if you obey that condition, then you can show that you will not, you'll get decent costs because this term is here, and you will eventually get samples that are close enough to pi theta that the distribution mismatch problem goes away. So this has nothing to do with the stability stuff. At least the reason this works, it does not rely on the stability. Yes?
So our intuition is that we can learn the most when extreme situation happens, but with this strategy we are avoiding those.
Not so much extreme as so you don't need to see really scary stuff. You just need to see the really scary stuff that your policy will put you into. So you don't need to see your car crashing into a truck if your policy would never do that. But if your policy might occasionally make you crash into a truck, then you need to see sort of yourself on the way to the truck, and then someone needs to catch you and get you out of there.
But if a truck is coming to you, your policy is not going to a truck, but the truck might come to you in some situation.
Well, yeah. So there's kind of another issue with all this stuff, and partly it's my fault for using autonomous driving as the example. There's sort of this rare events problem, which this says nothing about at all whatsoever. So all of this assumes that your conditions at training time are roughly representative of what you see at test time and all this stuff. So if there's some event that happens once in a blue moon, this won't save you. Yes?
So this looks like a very complicated optimization problem. How do you solve that efficiently?
This one here?
Yes.
Well, it actually turns out to be very similar to a standard stochastic optimal control problem. So this KL divergence term, it just ends up being an expectation under pi hat of log pi theta plus an entropy term. The entropy term turns out to be really easy to integrate into optimal control problems, and the other part is just, this is an expectation of a cost, this is an expectation of some other thing, so you can just add this to your cost. So essentially what this does is it augments the cost function with an additional term that says, take actions that have high log probability under pi theta. So the underlying optimal control algorithm is not new or particularly clever, it's just an off-the-shelf MPC method. Okay, so let me talk a little bit about kind of a little application of this that we evaluated. this is going to be in simulation, but it's meant to be roughly representative of a quadrotor. So what we did here is, we assume that at training time you can measure the state of your quadrotor. At test time you won't, and you'd like to be able to fly using raw sensory measurements. So your observations will be either a fan of laser rangefinders or black and white images from an onboard camera, and your state is going to be, the 6 DOF configuration of the vehicle. So there's this kind of input substitution trick where you use the state to actually train the policy, but then you force the policy to take good actions using only the raw sensor measurements. So the particular way in which this mechanism kind of avoids getting into trouble at training time is that if your current policy pi theta is not very good, and it's, let's say, approaching an obstacle, then this cost will become very large if it predicts that you'll hit the obstacle. So the pi hat will essentially override it. It will say, okay, I know you want me to do the same thing as pi theta, but you'll get a really bad cost, so in the balance with this objective, it's better to avoid the obstacle, even though that's not what pi theta would have done. That's kind of the test case that we have here. This is actually a 3D simulator. It's just shown overhead. And here you can see the quadrotor flying using the laser rangefinders, and it's dodging these obstacles. And then we found in comparisons that if you use kind of the standard DAgger method, you experience more high-speed collisions during training than you do using this technique. So kind of the short story with this is that, yes, you fail less during training, but you have this fairly strong assumption of requiring knowledge of the true state of the system at training time, which sometimes is reasonable and sometimes is not. And one of the things we've been working on since then is how to relax that assumption, but we don't quite have presentation-ready results on that just yet. So this is another example of flying through a canyon using, in this case, grayscale images. Okay. So let's now talk a little bit about situations where we might not know the dynamics of the system. So if you're doing something like driving a car or flying a quadrotor, it's kind of reasonable maybe to assume that you have a decent model of physics and you can kind of predict how your system will evolve. But if you're doing a complex robotic manipulation task, like let's say you have a robot that wants to fold a towel or pack some tight-fitting items into a box, then getting a very accurate prediction of how these objects will react to forces and so on is actually very difficult. We kind of understand how physics works, but identifying the physical properties of all these objects with enough accuracy to make good predictions is pretty tough. So for systems that look more like this, it would be awfully nice not to require knowledge of the dynamics, not to require knowledge of f of x t ut, and still be able to find a good policy. So it turns out that we can actually do trajectory optimization under unknown dynamics pretty well. This is not too complicated, but I just want to tell you about it just so that it's clear that this is possible. So again, this is our optimal control problem. We can substitute the f in there and make it an unconstrained problem if we want. And then the thing that we need is these derivatives. So if we don't know the dynamics of the system, then the thing that we're really missing is these derivatives. That's the thing we really ought to have. Basically, how will your next state change if your current state changes, or how will your next state change if your action changes? So these derivatives are just a linearization of your system. So basically, you need to be able to draw that line that tells you how will xt plus 1 depend on xt. And instead of trying to get these derivatives by actually differentiating known equations of motion, you can do something actually very simple that turns out to work quite well. So you can get your current guess at your stochastic policy ut given xt. Maybe initially you just set it to be random. Maybe it's a zero mean with some random noise. And you actually just run it on your robot, get some trajectories, and then just do something that looks like linear regression to fit this linearization. So instead of actually computing derivatives through your equations of motion, you'll just fit a plane to it and hope that that's close enough to your derivative. It's kind of a simplistic idea, and in its most basic form it doesn't quite work, but there's a little trick that makes it work very well. So if we assume that our dynamics look roughly like this, so they're stochastic, but they're basically Gaussian with some noise, linear regression will allow us to fit that. We'll do separate linear regression at every time step, so they're time-varying linear, which is a very expressive class of dynamics models. And then we'll just hope that that's close enough. That mostly works, but there's a little bit of a problem. So the true dynamics, of course, are highly nonlinear. So if you fit your dynamics with this linear regression method, and then you solve the resulting optimal control problem, you might go into a region where your linearization was completely wrong. And if you go there, then your controller might do something crazy, and your robot might damage itself, or your algorithm will diverge, depending on which of those things you consider as worse. So what we can do is instead try to bound how much the controller changes. Basically, try to bound how much the controller will change such that it stays within the region where your linearization was good. And a natural way to bound it, if it's a stochastic controller, is in terms of KL divergence. So we can actually, in this improvement step, we can just minimize the expected cost under the new controller, subject to a constraint that KL divergence against the old controller is limited by some epsilon. And we can dynamically adjust epsilon so that our dynamics approximation is good. And that actually turns out to work pretty well. So that allows us to do a whole bunch of interesting real-world robotic manipulation tasks without knowing the dynamics. So now we can do trajectory optimization, which means that we can plug this into our favorite imitation learning algorithms and use it to train some policies.
How do you choose epsilon there?
So epsilon, right now, we don't have sort of a really good way to choose it, but we have a really good heuristic that dynamically adjusts it based on whether or not your current guess at the dynamics, if you then use your current estimate of the dynamics, if you use that estimate to compute the expected cost and then compare it to your empirical cost, depending on how far off you are, you can dynamically adjust it, and that actually ends up working pretty well. There's a little bit of a model underlying this that says basically how much your difference in cost will depend on epsilon, and you can do a little bit of stuff there, but it's basically a heuristic. Just a pretty good one.
Sorry, what's tau here?
Trajectory. So tau is state, action, state, action, state, action.
Sequence.
Yeah. Okay. So here's a video of this algorithm actually running on a robot. So every time you see it move and then reset, that's one trial. So that's one trajectory. It takes 5 trajectories per iteration, refits the dynamics, updates the controller, and then runs that controller again. So this is just doing the trajectory optimization with unknown dynamics. And this is kind of one of the building blocks that you can then use to learn more complex policies. And hopefully you figured out here what the robot is trying to do. So as it proceeds, it gets better and better. Yes?
So you showed before some examples where you knew the state, like flying through
Yes.
the trees. How do you do if you don't give it the state information and use this algorithm?
So this still requires the state information. It doesn't require the dynamics.
Okay.
So the state here is the joint angles of the robot, the velocities of the joints, and the position and velocity of the end effector.
Okay, but if you don't give it the dynamics in the tree flying thing and use this algorithm, does it do comparably or much?
You can do that. The main issue with this algorithm, this is a very good question actually. So you generate some samples and then you fit a linearization to them, right? So if these samples are all pretty close together, then doing linear regression to fit the linearization works fine. If these samples are all over the place, one of them goes here and the other one goes way over there, you try to fit one line to them, you're going to get some horrible garbage. One way you can mitigate that is you can say, okay, well, the reason that I mentioned this is because in the quadrotor case, maybe one of them collides with the tree and the other one doesn't, right? So you run it 5 times, 2 out of the 5 collide, 3 don't. You try to fit a line to the ones that collide and the ones that don't, and you're in bad shape. There's a little trick that you can do to fix this. You can basically just cluster the trajectories and then fit the linearizations. That works fine. We haven't tried to do it on an actual quadrotor yet, but we have done this clustering trick with the manipulation tasks. Okay, so let's talk about how we can combine this with policy learning. We can't quite use the PLATO algorithm at this stage because PLATO iteratively replans, but we actually don't have to because we have a little bit of an advantage here. So because we generated our dynamics by running a bunch of samples, we know not only the states along these trajectories now, but we also actually know the observations. Whereas in PLATO, we didn't know the future observations because we couldn't predict them. So on the one hand, we can't iteratively replan because we need to generate a bunch of samples just to get one trajectory. On the other hand, we actually don't have to because we have the observations along this trajectory. So here is an algorithm that we can use together with this trajectory optimization procedure to actually train a neural net policy that uses observations. So this is called guided policy search. And it's going to go something like this. So our goal in the end is to minimize expected cost under our neural net policy. And we can rewrite it as an equivalent constraint optimization where we're minimizing expected cost under the trajectory distributions induced by these linear Gaussian controllers, subject to a constraint that their probability over actions is equal to the neural net's probability. Okay, that kind of makes sense. So if the probability over actions is the same, then these are the same distribution, so their expected cost is the same. So that's our trajectory distribution, and we're just saying their actions should be the same. And then we do something fairly simple. Well, first we rewrite that constraint. There are a few different ways to rewrite it. The problem is that this is an infinite number of constraints because there's infinitely many states and actions. So we need to rewrite it in some way so there's a finite number of constraints. There are a few different ways to do it. One that's pretty simple is to just say the KL divergence should be 0 between these two distributions, and then you just have one KL divergence constraint for every time step. So I'll just, for the sake of conciseness, I'll just write it like this, like D. So D says the KL divergence between pi theta and P at time step T is 0. And then you can just write down the Lagrangian of this problem. So there's your objective, there's your constraint with a Lagrange multiplier, and then you can use something like dual gradient descent to solve this. So you basically just alternate between minimizing the Lagrangian with respect to the primal variables, that's the trajectory and the policy parameters, and you can do this in a kind of a block fashion. So you first minimize with respect to the trajectories, that's that model-free trajectory optimization. Then you minimize with respect to the policy parameters, which is just supervised learning. It's basically minimize this divergence with respect to the policy parameters. Supervised learning with your favorite supervised learning method. And then you increment your dual variables. And then you can repeat this process, and that will drive this constraint to be satisfied, and therefore minimize the expected cost of your policy. So that's one way to do it. There are a few variants of this algorithm that make a few different modifications for the sake of better convergence results, but basically this is the overall scheme. So this is called guided policy search. At a schematic level, so that was kind of the equations. At the schematic level, what it's doing is basically this. If you have, let's say, a task, here the robot is trying to put this little red shape into a shape sorting cube. You pick out a few initial states of this task. So for the case of this problem, there's different initial positions of the cube. For every initial state, you optimize a different trajectory using that trajectory optimization algorithm. And that's what that looks like. So the robot is just moving the cube to different initial states. For each one, it's taking 5 samples, improving the corresponding trajectory, and then moving on to the next one, and it does this in a loop over and over again. That gets you training data. You use that training data to train your neural network using supervised learning. This neural network is not given the position of the cube, it's just given the camera image. And then you repeat the process because you need to do this through this dual gradient descent procedure. So you increment the dual variables and then go in and re-optimize your trajectories. So intuitively what's happening here is that the trajectories are being modified to get better cost and to come closer to what the neural net policy is trying to do. And the policy is just repeatedly trying to follow the trajectory optimization procedure. So this thing, the trajectory-centric RL or trajectory optimization is just trying to solve the actual control problem, and this thing is trying to generalize. And because it's trained using the observations rather than the states, we can do something like have a person then hold the shape sorting cube, and if we run the neural net, it can just use the images and figure out where it is and perform the task. Okay, so this is kind of the flow chart of the method. So run your trajectory on the robot, collect the data, fit the dynamics with linear regression, improve the trajectory, and then repeat. And then the same data can be used to train the neural net from observations rather than states. And that's also included in the cost function so that you get closer and closer to the neural net. So that's kind of the sketch of this algorithm. Okay, so does anybody have any questions about this? Okay, great. So I already talked about the fact that the neural net is trained from observations. I can show you, I'll skip the details of the neural net architecture because there's another talk on deep learning later in this workshop, so this is kind of maybe a topic for another time. But let me just show you a few of the results, just so you get some idea of what's going on here. Okay, maybe my video isn't playing, but it looks a lot like the Lego example. So I'll, in the interest of time, I'll talk about the next stage, which is reinforcement learning. So first, let's conclude this with a few concluding remarks. So, one of the questions about this class of techniques where you're using a control algorithm together with imitation learning to learn a policy is, is it actually any different from standard imitation learning? So if we want to design algorithms of this type, is it just a matter of designing good imitation learning algorithms and then substituting an optimal control for the human, or is there more to it? There might be more to it because when you're using optimal control to generate the data, you can actually change the behavior of the teacher programmatically. And we saw that in the case of PLATO, where this optimal control teacher actually had a term that accounted for the divergence against the learned policy. And we saw that in the case of guided policy search, where trajectory optimization actually changes behavior to come closer to what the neural net was doing. So if we consider sort of these imitation learning algorithms that are learning from a computational teacher, there's some interesting stuff we can do in playing with what the teacher is actually doing and figure out like what is the data the teacher should generate in order to maximally help the learner. And then the other question here is, well, can the policy that you're learning actually help optimal control as well? So in the methods that I presented, it was sort of optimal control was generating the training data, and the policy was just trying to follow along. But in reality, you could probably also use the policy in some way when you encounter a new problem to help optimal control get started. And we didn't see any of that in the methods I showed, but I think that's something in the future that would be really interesting to explore. Okay, so now let me get to the last technical section of this talk and talk about reinforcement learning. So here we're going to change gears a little bit, and instead of even attempting to fit the dynamics, we'll actually work with algorithms that don't even require an estimate of the dynamics and are completely model-free. So in this class of methods, we won't attempt to learn p xt plus 1 given xt ut. We'll just attempt to directly optimize policies. So first, I'll show you a very simple reinforcement learning algorithm. It's called the policy gradient algorithm. And then I'll talk about a number of different modifications we can make to it to make it practical for use with large function approximators like deep neural nets. So this part is all background, but I think it's mathematically actually quite elegant and good to understand. So just to remind you, the problem we're trying to solve now is we're trying to minimize the expected cost, so it's the same as before. And now we're going to try to do this without actually trying to fit the dynamics distribution. So how can we do that? Well, we can write down our distribution over trajectories. For the sake of notational clarity, we'll just say that this is an expectation with respect to this distribution over trajectories of the total cost of that trajectory, which we'll just abbreviate as C of tau. So keep in mind that inside the C of tau, there's actually a sum. And this thing, you can decompose it over time steps. But for now, just so that I don't have the summation symbols everywhere, we'll just operate at the level of trajectories. And if you're ever in doubt as to what a trajectory distribution is, it's just this thing. It's just the product of all of your unknown dynamics and your policy and your initial state. Okay, and we'll call this thing J of theta. So it's your total expected return of your policy depends on the policy parameters theta. So theta might be the weights in your neural network. So, well, if we want to optimize something like this, perhaps all we really need is to compute a gradient. And we can do that. So we can write down the gradient of J. It's the gradient of this expectation. We can write out the expectation as an integral. We can put the gradient operator inside here because the only term that depends on theta is p theta. And then there's a really elegant trick that we can use to derive a policy gradient, where we just note that grad p theta is p theta times grad log p theta, because grad log is 1 over p theta, grad p theta. These cancel out. So that's a really neat identity. We can substitute this really neat identity in here. And we get this. This is just an expectation under p theta. So now we've arrived at this equation. So the gradient of your return is the expectation of the gradient of the log probability times the cost. Which is nice because these kind of expectations you can compute just by taking samples from your policy. So now we're going to go back to this notation with states in action. So we'll substitute this equation for p of tau in here. So that gives us kind of quite a mess. But, so I just replaced p of tau with this thing. It's quite a mess, but most of the things in here don't depend on theta. So you can kill this part, you can kill this part. The only part that depends on theta is log p theta, or log pi theta, you given x. So these parts both go away, and you're just left with a very simple equation that's just the sum over all time steps of the gradient of the log probabilities under your policy. So the dynamics have vanished now. And now you just take this thing, you substitute that in here, and you're left with this equation for your gradient, and the dynamics are nowhere to be seen. So this is kind of a neat trick. This was I believe originally proposed by Williams in 1992, although perhaps even before that. And this is a very standard kind of reinforced policy gradient method. There's a little bit more that we can do to make this into a practical policy optimization procedure. So before I get into that, let me just give kind of a concrete example of an actual policy you might use. So for example, if we have a continuous control problem, our policy might be a Gaussian, conditional Gaussian, where the mean depends on the state, maybe through some complicated function like a neural network. That means that the log probability is just the squared difference between the action that we took and the mean of the neural net under the covariance. So we can compute a gradient of it and everything is all good. And then we can plug this into a standard backpropagation neural net optimizer. So this is all very simple. So you can use a standard neural net package for that. So the schematic of this reinforced algorithm is just you sample your trajectories by running your current policy on your physical system, on your robot or whatever. You estimate this gradient using the sample, so it's an expectation, which means that you can do a sample-based estimate of that expectation just by summing together these grad log pi times the cost of that sample. So basically weight each of these by the total cost of that sample. And then you just increment your parameters and just do gradient descent. So everything is pretty straightforward, and then you just repeat. There is one more piece that is really, really important to make this work well. It's not quite obvious why it's important from the way I wrote it, but here's that piece. It's called a baseline. So before I tell you how the baseline is incorporated into this, let me just prove a little identity for you. So if you have an expectation of grad log pi of some constant b, we can write that out like this. So I just wrote out the expectation. Based on that identity that I showed you before, that's just grad p, which means we can take the constant out. This part is the gradient of the integral of py, which of course is 1 because it's a distribution. So it's b times the gradient of 1, which is 0. So that means that in here, I can add or subtract any constant b, and in expectation, this value won't change. So in expectation, it won't change, but the variance of the estimator will change. And in fact, I can choose b so as to reduce the variance of this estimator if I'm using a finite number of samples. And that turns out to be a really, really useful trick in policy gradients. In fact, a lot of current research on this topic is looking at kind of interesting ways to choose the baseline b. But in the simplest case, you can choose a constant, and that already will go a long way to reducing the variance of your gradient. So that's just a really useful trick. There are optimal choices for this baseline, which I'm not going to get into in this talk. But as a simple rule of thumb, a good but suboptimal choice is to just take the average cost. So you just take the cost of the current sample and subtract the average cost of all your samples. That works pretty well. It's not the optimal choice, but it's a pretty good one. And if you do that, then there's a very natural intuition to what this algorithm is actually doing. Let's say that you generated some samples from your policy, and some of those samples are good, that's the green check mark, some of them are bad, that's the red X, and some of them are sort of mediocre, that's the orange check mark. And since they were samples from your policy, maybe they had about equal density. If you use this estimator, what it will basically do is it'll say the good sample should become more probable, the bad sample should become less probable, and the average one should roughly stay where it is. So if you use this average cost baseline, that's basically what you're doing. Say the sample that's better than average, make it more likely, the sample that's worse than average, make it less likely, and deal with the stuff in between, sort of proportional to how much better or worse it is than the average. So that hopefully gives you some idea of what this algorithm is doing. It's a very kind of classic sort of trial and error method. If you did better than you expected, then make that more likely. If you did worse, make it less likely. So that's sort of one of the standard RL methods. Now, unfortunately, the story doesn't quite end there. So this kind of likelihood ratio policy gradient method in its kind of vanilla form often is not so great when you have to deal with really high dimensional policy classes like deep neural networks. So it typically gives you a very high variance estimate of the gradient, even if you use a clever baseline. Smarter baselines can help with that. So for example, you can have B depend on the state. You can even have it depend on the action, as I'll talk about later, but that gets a little more complex. You can have some problems with poor conditioning. You can, sometimes using higher order methods like natural grading can really help with that. It's very hard to choose the step size for reasons related to the 2 points above. So trust region methods where the step size is chosen so as to bound the change in the policy can be really helpful there. So this is a method called trust region policy optimization. This is something that we developed a couple of years back. That tends to work pretty well. It's kind of a combination of natural gradient and trust region. So you actually choose the step size so that your policy changes by a fixed amount in terms of KL divergence. I won't get into the technical details of that, but that was one of the methods that seemed to work fairly well for some very large policy classes. Okay, so that's policy gradients. Now let me talk a little bit about value functions, and then I'll put these pieces together. So, and this may be something that Emma talked about earlier in the day. But one of the things you can do is you can take your policy gradient and you can rewrite it a little bit like this. So I just took the sum out of the expectation, and now you have this funny term. You have the gradient of the log probability of an action at time t times the sum of costs from time 1 to the end of the horizon. That's kind of funny. The action you take at like time step 50 is not going to change the cost that you incur at time step 49 or 48 or so on. So you can actually incorporate your knowledge of causality into this, and you can remove all the costs that came before the current time step. So you can rewrite a slightly different form of this estimator that's still consistent, that takes the gradient of the probability of an action at the current time step times all the costs from now until the end of time, ignoring all the costs that came before, because changing the action at time step t is not going to change your cost at time t minus 1. And if you do that, well, first you get a better estimator. And in fact, you can put the expectation operator here. You can say that this is the expected cost from now until the end of time. So this is the total remaining cost of executing pi theta. And now this has like a fairly natural interpretation. You're saying that I'd like to change the probabilities of my action based on the expected cost that I'll get from here until the end of time. And this expected cost is what's called the Q function. So if earlier in the day you heard about the Q function, this is basically the same thing. The Q function is the cost that you'll incur if you take a given action in a current state and then follow your policy. And sometimes it's written as Q pi there, just to denote that it's the Q function for a particular policy pi. So it's the total cost of running pi. And we can actually write the Q function in this form. We can say it's the cost now plus the expected value function later, where the value function is the total cost if you start from that state. So we can kind of expand out these terms. We can say, okay, Q function, the cost now, plus the expectation over the next state of the expected action under your policy of the next Q function. And this term right here, this is the value function, this expected Q given the action distributed according to your policy. So these are useful objects that we're going to then use to incorporate into our policy gradient or to design algorithms that don't even require a policy gradient like Q-learning. Okay, so well, the first thing we can do is we can say, okay, we have this expected cost. We can just substitute an estimate of the Q function in there. We can get this estimate using Monte Carlo. That's essentially what policy gradient does, just average together a bunch of samples. But we can actually also try to fit a function approximator to this Q to try to reduce the variance of this gradient even further. So we can say, okay, we'd like our estimated Q values to be close to this expectation of costs. And we can just do this with regression. One way we could do it is we can actually just run our policy and regress to those sums of costs. Or we can use so that we can regress to the sums of cost. Or we can use the identity that I showed before, where the Q function is the current cost plus the next Q function, and get an even better objective for training these Q values. So we can say that, well, we'll find the Q values that minimize the difference between Q and the cost plus the next Q. Oftentimes it helps to introduce a little discount factor in there, a little value less than 1, just so that these sums actually converge. Because for infinite horizon problems, they might not, in general, be finite. So and this quantity, by the way, is called Bellman error. So you can use this value function approximation inside your policy gradient. You can, for example, sample some trajectories from your current policy, use those samples to fit your Q function, and then incorporate that fitted Q function inside your policy gradient. And this is what's called an actor-critic method. So basically, we substitute the sample estimate of the cost for this fitted Q function. And then we update our parameters as usual. Now, there are some challenges with using value functions and actor-critic methods as well. Many of them are the usual problems with policy gradients, so we'll inherit many of those, although our variance will typically be lower because we're directly trying to estimate this expectation. It's still hard to choose a step size, etc. We have to make this bias variance trade-off. So when we have our standard policy gradient, it's unbiased, but it might have high variance. The one where we use the function approximator, it's hopefully going to have lower variance because we've directly tried to estimate this expectation. But generally, we won't get it completely correct, so we might have some bias because our regression, we don't typically solve regression problems perfectly. We'll have some epsilon error, and that might cause some problems. So it's a bit of a bias variance trade-off. There's a way to actually blend these two, so you can actually make kind of a weighted combination of the Monte Carlo version and the function approximator version, and that's explored in this paper on generalized advantage estimation. And then you have potentially some problems with instability and overfitting when you fit this Q function. So you can use some trust region methods when fitting the value function so that it doesn't change too much iteration to iteration, and that can also fix some of the instability issues there. So if you use a combination of Monte Carlo estimates and fitted value functions with policy gradients, you can actually solve some fairly complex tasks. So this is a 3D bipedal character learning how to run, entirely using reinforcement learning without any estimate of the dynamics, just using a policy gradient method with an estimate of the value function. And it actually tends to work pretty well. There's also been quite a bit of work in deep learning and deep reinforcement learning on using these for more online actor-critic methods that instead of operating on these batches, actually update the policy directly online every time step. So instead of sampling a whole bunch of trajectories from your policy, they just make one decision, take one time step, add it to a buffer of data, sample a mini batch from that buffer to fit their function approximator for the value function, and then use that batch to modify their policy and then repeat. So these methods would actually change the policy every single time step. And one example of this is a method called deep deterministic policy gradient, which is a fairly effective online actor-critic method that uses this replay buffer. But the theory underlying that is very similar to the policy gradient stuff that I discussed. So the other thing you can do is, if you're going to fit a Q function anyway, you can just omit the policy gradient completely and try to just directly use your Q function to make decisions. So this is the Q algorithm, the Q learning algorithm that I think was described earlier in the day. One of the small changes you have to do here is, instead of estimating the Q function of the current policy, you can actually estimate the optimal Q function. So over here, instead of taking the Q value at the next step, you can actually take the Q value for the best action. So you can replace this with a min. And this is the objective for Q learning. So then your policy is just some result of your Q function. For example, it might be the exponential of the negative Q function, or it might be just epsilon greedy, which means that you take the best action with probability 1 minus epsilon. With probability epsilon, you take a completely random action. There are a few different choices you can make here. And then you just forget about the policy gradient entirely and just rely on your Q function. And that's Q learning. So in Q learning, you make a decision, add that observation to your buffer, sample a mini batch, update your Q function using this objective, and then you act according to your Q function. So that's Q learning.
So why this proportional to e to the minus Q? What's the...
Oh, that's an interesting question. Yes. So this by the way is a more popular option. This is a kind of an interesting option. So you can actually interpret with a little bit of additional probabilistic machinery. Yeah, you can interpret this reinforcement learning problem as trying to match a distribution, which is proportional to the exponentiated negative cost of your trajectory. And then, if you do that, it turns out that this is the optimal answer. And that problem basically corresponds to the classic reinforcement learning problem with an additional term that says you should minimize cost but also maximize entropy. So basically try to hit the low-cost regions, and if they're all roughly equal, try to hit as many of them as possible. And in that case, this actually turns out to be the optimal solution, which is kind of neat. So you can view that as basically a more principled way to break ties, right? So in a deterministic policy, you basically have to get the best trajectory, and if a few of them are equally good, you just arbitrarily choose one. And with something like this, you would sample your trajectories with probability proportional to how good they are. Anyway, there's sort of a bit more hand-waving I can do about that, but that's maybe something we take offline. So the reason, part of the reason I mentioned Q learning is because it was actually popularized by this, fairly well-known work on using Q learning for playing Atari games from Google DeepMind, where they used this algorithm to play a large number of games from raw RGB images. So that was the algorithm they used. You can actually do a continuous variant of Q learning. So this minimization, that's typically the main thing that causes some trouble. So in discrete settings, you can just enumerate all your actions. In continuous settings, it's a little tougher. But you can actually choose a representation for your Q function. So that's in discrete settings. You can choose a representation for your Q function that makes this minimization easy even in continuous spaces. There are actually a few different choices you can make, but one of them is that you can actually output a Q function that's quadratic in the action. So you can just say, okay, I'm going to have my neural net, and it's going to output a matrix and a vector and a scalar. The scalar is just the value part. The matrix is the matrix under which I'm taking this Euclidean norm. And the vector is where it's centered, and then you know that the minimum of this with respect to u is just going to be mu of x. So that way you can actually apply this for continuous spaces as well, and that can be really convenient. And this is of course not the only function that's easy to minimize with respect to u. You incur a little bit of a loss because this may not be as good at representing the true Q function, but it's nice because you can do this minimization very quickly. So I'll skip this result, but one of the things I want to show you is a result using that method. This is basically Q learning in continuous spaces using these easy to minimize representations where it's quadratic in the U. And this is a result where we ran this on a bunch of real physical robots. So this is a deep neural network that's actually parallelized across multiple robots using this continuous Q learning to learn how to open a door. So that's kind of nice because that that shows that the algorithm is actually fast enough to use on real physical systems. It took about 2.5 hours with 2 robots, so it's quite a bit slower than the method I showed before, but it does actually do this fairly difficult task. This part I'll skip because I'm kind of running a little low on time, but one of the things I wanted to talk about is some of the trade-offs between the imitation learning methods that I showed before and reinforcement learning. So one of the trade-offs is sample complexity. Generally, model-free reinforcement learning methods, especially when used with deep neural network function approximators, tend to be quite data hungry. And that has been actually a major challenge in applying them to real-world problems. So the Q-learning method that was used for learning the Atari games used about 100 hours of, if it were running in real time, it wasn't running in real time, but if it was running in real time, about 100 hours of experience to learn the game of Breakout. The algorithm that I showed you before that was learning how to walk, that took the equivalent of 50 hours of real time, if it was actually real time. Of course, everyone runs these things on a server, and they run faster than real time, but if it was a real robot, it would be 50 hours. The online actor critic style methods and the Q-learning methods tend to be a bit faster. So like things like the basic manipulation tasks that I showed before, that was 2.5 hours with 2 robots, so the equivalent of 5 hours of experience. Walking you can typically get in 4 to 5 hours. So it's on the order of single digits of hours. The model-based methods tend to be quite a bit more efficient. So the time-varying linear model stuff that I showed before with linearization, that took 3 minutes of experience to learn a real-world manipulation task. So it's substantially faster. And with 30 to 40 minutes, you can actually learn the shape-sorting cube task with vision. So if you're actually fitting a model, provided it's chosen intelligently and carefully, you can do much better in terms of sample complexity. With these things, the nice thing is that you're making fewer assumptions about the system. So if you want to, let's say, fit linearizations at every time step, that's making some assumptions about continuity. If you're just using a model-free method, you don't need that assumption. So that's kind of the trade-off. But the gap in sample complexity is quite large. And this is just showing the number of trials for a number of different tasks learned using vision with the guided policy search method. And this is the total number of trials, each of which is 5 seconds in length. So there's quite a gap in sample complexity, and actually a big area of research now is how to close that gap, basically how to make these guys faster, or how to relax some of the assumptions for these guys. And of course, there's some interesting work being done at combining ideas from both model-based and model-free methods. Specifically, how can you basically get the speed of these guys over here, but still kind of revert to a model-free behavior towards the end to really reach the optimal cost, even if you're not fitting a good model. So yeah, this starts summarizing what I already said. So the benefit of reinforcement learning generally is fewer assumptions. You don't need to model dynamics. You don't in general need state definition, only observations. So you can run policy gradient directly on observations. And it's fully general in terms of stochastic environments. You don't need to assume continuity and things like that, but much slower. And sometimes hard to stabilize. So some of these algorithms are a little difficult to make stable. OK, so I'm just about done. One of the things I wanted to leave you with is a neat little video that talks about kind of some of the frontiers in this area. One of the things that really made a big impact in regard to deep learning is that deep learning methods, at least in computer vision, showed really nice results as far as generalization. So you could train, let's say, an object classifier on the ImageNet data set, and it would be able to classify objects it's never seen before with very high proficiency. So when it comes to deep robotic learning, whether it's reinforcement learning based or imitation learning based, one of the questions that we could ask is, well, what is it that we need in order to get the same degree of generalization? And we could look at the things that have contributed to getting good real-world generalization in supervised learning. They include things like availability of large amounts of computational power, improvements in algorithms and models, of course, but also the availability of large amounts of data. And that third point is, of course, very, very important. So when it comes to learning sensory motor skills or learning robotic behaviors, one of the things that we need to think about, besides computational algorithms, is how we're going to get large amounts of data. Part of the story is having algorithms that can actually learn and behave safely during training time, related to that point about PLATO earlier in the talk. But part of it is also scaling up in parallelism. So one of the experiments that I worked on recently, and I just wanted to show you this video towards the end because it's kind of interesting, is to actually run large-scale parallel reinforcement learning on large numbers of robots. So these are robots that are all working together to collect data for grasping, and we had some experiments on those that show actually some pretty interesting results. I'll skip over the details here, but one of the cool things we can see, other than the numbers being nice, is that when we actually run the policy that we learn from large amounts of experience, it actually exhibits some interesting habits. So here I'm going to show you a collection of objects that are all visually kind of similar. They're all blue and roughly rectangular. And for the rigid objects, the robot learned to adopt a fairly natural behavior. It just puts the fingers on either side of the object. But one of the things it learned actually fairly quickly is that when the object is very soft, like the sponge here, it's actually much more effective to just pinch it in the middle. And this is not an accident. This is actually pretty consistent. So you start to see these effects once you can collect enough training data and enough experience of fairly realistic scenes that you get these emergent behaviors where the robot figures out some pretty interesting stuff. This is an object that's very heavy, so it's important to grasp it in the middle. This is an object that's very flat. It's low to the ground, and that's very difficult for traditional robotics methods that use depth cameras. And here again, you can see it takes a little while to figure out a good grasp. What it's really doing there is the method is kind of similar to Q-learning. It's actually estimating the probability of success. So it's moving that gripper until it finds a state for which it's predicting good chances of success if it picks up the object. So this is an object for which you have to grasp it both in the middle, and it's also very heavy. This one is transparent. One of the problems that comes up in real-world applications, sorry, I'll play that in a second. In real-world applications of reinforcement learning is that oftentimes actually evaluating the objective, evaluating the cost function is itself very difficult. So in all the discussion I had previously, we sort of assume that the cost function is just given to you and you can evaluate it. But in the real world, that's often not an assumption that you can make. For example, if you want to learn to pour things from one cup into another, just being able to detect that you're actually pouring things successfully requires a complete computer vision system. So if you're going to build that system in the first place, then it doesn't really, you've already solved basically half the problem. So one of the things that we've been working on is actually learning the cost function using some visual features. So if we have, let's say, a person demonstrating this, this is the inverse reinforcement learning that I mentioned earlier. Can we analyze those demonstrations and actually figure out a cost function in terms of some visual features or in terms of the observations? So that's one way we can kind of bridge that gap. So if the person demonstrates it, then maybe we can have a robot that can use that cost to then solve a task like this. This part I'll skip over. And then, yeah, I guess the last thing I want to leave you with is a few points about some challenges. So let's see here. Right. So there's a number of challenges in terms of algorithms as far as sample complexity, safety, as in the case of things like PLATO, scalability, if you wanted to run on multiple robots, multiple physical systems. There are challenges in regard to supervision, in terms of evaluating success, learning cost functions, and so on. And a few of the challenges not mentioned here are the theoretical challenges as far as understanding it, especially in regard to imitation learning, which situations you can expect it to work in and which situations it might not work in. In regard to reinforcement learning, how can you actually ensure that your policy grading method will actually achieve an improvement and so on. So these are many of the frontiers in this field, and I think there's a lot more to do here. All right, so I'd like to acknowledge my collaborators, and I'd be happy to take any questions. Yes.
So you haven't talked much about exploration.
Yes. Well, if you gave me another 90 minutes, I probably could, but I'm kind of... yeah, so that's a very, very good question. So exploration is an important question in many of these areas. And actually, if you remember the door opening task, that one, actually part of the reason why we actually used the Q-learning based method for that is that it actually does quite a bit better in terms of exploration than the model fitting approach. So there you can give it, in that case it was just random exploration using that Boltzmann style thing. But what it does is if it kind of accidentally experiences one success, it'll actually pick up on that and then reinforce it further. With the model-based approach, basically all you get out of it depends on how good your model is. So if you get one success and like 9 failures and you fit a model to it, you won't necessarily visit that successful region over and over again. But doing things more explicitly with exploration can go a long way. So one kind of family of exploration methods that's proven to be pretty effective in the last couple of years is based on generative models. So you can actually fit a generative model to, let's say, the states that you're visiting or the actions that you're taking, and then try to use some measure of the surprise of that model. Basically, if you observe a state for which the model assigns a low probability, you can use it as a measure of your surprise and assign an exploration bonus. Basically, add a little value to your reward to encourage the policy to visit those states more. So that class of methods has been explored in various instantiations of it have been explored in recent years and seem to be working fairly well. But that's a very active area of research right now. Yes?
So one of the things your sort of the earlier part of your talk suggested that maybe the better way to train many of these models is to introduce perturbations during training. So for example, you could imagine a car being once in a while accidentally being steered randomly, and so I wonder if any of these systems actually use this sort of
well, that's essentially like very closely related to the question earlier. So in reinforcement learning systems, typically they do actually intentionally inject noise for the, sort of the terminologies that it's used for the purpose of exploration to visit new states. But really the effect it's having is very similar to what you just said, is that you experience some things that are maybe closer to mistakes so that you can figure out how to correct them, so that you become more robust when you actually act in the real world.
No, but I meant specifically for stabilizing, not for exploration. I mean, this is slightly different. I mean, I'm not suggesting that you jump, you introduce something completely crazy.
Yeah, so actually, there's a little bit of stuff that we did in regard to this trajectory optimization algorithm with unknown models. As far as how you construct this stochastic controller, this may be something better taken offline, but there's something fun you can do about the curvature of the Q function to actually choose which areas you can go into where you want to be as random as possible while still avoiding the really, really bad stuff. So there's a little bit of fun things you can do there, but it's probably a longer story. Yes?
So these kind of systems, I mean, it's hard to see where to begin to do any theory because, I mean, everything is sort of put together, like everything is thrown together, right? So what do you suggest is a good place for theory?
So that's, yes, that's a very good question, and one that I've kind of struggled with a little bit. I think one thing that can be super helpful is some notion of, at least like, for example, in the context of imitation learning, something like a set of assumptions under which we can actually say something concrete about, let's say, the performance of standard imitation learning without any kind of data augmentation. Now, maybe we can't say concretely whether those assumptions are always satisfied with real human data, but at least if we know what the conditions are, then we could at least use that as guidance to how to structure our data collection and so on.
So maybe could you walk us through a sort of ideal theorem or something that you would like to see? Like under what assumptions to make and...
Yeah, so for example, in the case of imitation learning, if we have something that says, let's say, your expert is behaving according to some policy, pi star. Maybe you don't know what that policy is, but let's say we have a policy pi star, and that policy satisfies some conditions such that, for example, if we put it in a particular state, it will go to states that have, let's say, bounded cost, or it'll stay within some constrained region. And if you can say something like, if your expert satisfies this condition, then imitation learning will have, bounded loss, bounded regret. That would be a pretty good thing to have. And then we could, maybe we can't prove that a human will actually do that. But at least if we know that that's the condition, perhaps we can check it. Perhaps we can take a data set and check if this, how likely is this to hold and things like that.
Is imitation learning just a single algorithm, or you are allowed to...
Imitation learning is a class of techniques.
Class.
Yes.
You could design your own.
Yes. Yes. But there are different properties that an imitation learning algorithm can have. So DAgger is an imitation learning algorithm, but it requires you to collect additional data. The NVIDIA thing that I showed, that's just using a very, very simple, naive imitation learning algorithm where you just take your data set and you train your neural network on it. That's also an imitation learning algorithm. It's a simpler one without any concrete guarantees on performance, but fewer assumptions because you don't need additional data. Yes?
The fact that robots are acting slowly, is it because of the optimization that is running in the background?
Okay, so that's a good question, yes. So especially the robot that I showed in the beginning opening the door was moving very slowly. There are a few reasons for this. In the case of the video from the DARPA Human Robotics Challenge, there's a very practical reason, which is that there's a bunch of people sitting in a back room sort of approving every decision, so they don't want it to go too fast. But maybe a more nuanced answer is something like this, that if you are using an algorithm, a control algorithm, that assumes some model of system dynamics, maybe something about physics, and that model is not very good, typically if you move slowly, the model will be less wrong. So there's a bunch of dynamic effects that you're not accounting for, complicated friction properties of the arm and so on. And if you go slowly enough, the error due to not modeling those effects will not be as big. So sort of the deeper answer to your question is that that's often the reason why, especially robotic manipulators, move slowly. Yes?
So these model-based and model-free frameworks seem, to me at least, to be sort of, well, different fundamentally.
Sorry, what?
Sort of different fundamentally in a number of ways, and you mentioned trying to bridge that gap. That's another question. So what are some ways that you envision closing the gap between those two approaches?
Yeah, so there are a few ways to do this. One very classic approach that bridges the gap between model-based and model-free is what's called the DINA algorithm. And what that method does, actually very simple. You fit a model of the dynamics to your data, and then you generate a bunch of artificial rollouts from that model. So you need to generate some samples in order to compute the policy gradient. Usually you would do that by running something in the real world on your robot, but here you're going to fit a model and just generate fake synthetic data from that model. That's a fairly straightforward and simple way. Now maybe there's more to be gained from kind of a more nuanced approach where you integrate these methods more closely, but that's just kind of one example.
All right, maybe we should excuse me, stop there and thank Sergey again.
It's enjoy it. So should we have a beer and